6.5, 6.4, and 6.6. Any questions? I did get lists of names of people who did the study back in the surveys just a little while ago. It does take a little while to compile to see who did all 3 items. Hopefully by tomorrow I will have that added onto your exam score. In addition, on Friday, I'm going to wait for that last attendance for this week's CSI, meaning next week Monday, I'll put the CSI points also on your exam score. So just, so you know, that hasn't gotten forgotten about. We good to go? We'll be doing some slide work for a while, so that one side of the room that we look at an easy little thing. I'm going to put the PowerPoint on the center screen as well until we need to actually use our paper. So that'll just take a second to get in there. Recall that we are teaching this chapter a little out of order, 6.1 to 6.3, then 0.5, 6.4, and 6.6. I didn't want that to be confusing in case you forgot from Friday. So we're starting up on number 1, page 186. If my computer wants to listen to me. There we go. We're looking at different types of energy. You do have a table. Radiant energy is, of course, the energy coming from the sun. It's our primary energy source for the planet. We have thermal energy, which is energy associated with the random motion of atoms and molecules. There is chemical energy, the energy stored within chemical bonds. We have nuclear energy, the energy stored within the collection of neutrons and protons in the atom. And we have potential energy, the energy available by virtue of the object's position. Do you recall that very first day of instruction where we went through the 4 fundamental forces? And we said, I'm not going to ask you these, but it's just so you knew where our focus was. The only purpose of this, I'm not going to ask you to define these, is so you know where our focus is. Which ones do you think is more important for chemistry? Chemical energy? Any others? Nuclear? If you do nuclear chemistry, true. Not this class per se. Thermal energy, the energy associated with the random motion of atoms and molecules. 6.1 through 6.3 and 6.5 is associated with thermal energy, whereas we get to think about chemical energy for 6.4 and 6.6. Another reason for the reorganization of those sections. If you're doing nuclear chemistry, yes, nuclear energy would be important. We don't do that in this class, so not that big a deal for us. So our focus is going to be thermal and chemical. Just so you kind of know where our focus is, the whole purpose why we're doing this. So if we want to think about the energy associated with actual atoms and molecules, your second table, number 2, is helping you think about that. The particle diagrams are on the screen. By term, it means, like for translational, it says E sub k, comma, trans. So that would be the term, the variable for that. So we have translational energy with moving particles. If they're moving, it is translational energy. If you have a molecule, the bonds actually are rotating, meaning what's attached to each side can move. And that's actually really important in organic chemistry. Vibrational energy, well, bonds are also like little springs. And we can use the vibrational energy of the bonds to tell which atoms are attached to each side. Something you'll actually investigate also if you take organic chemistry. Electronic, the motion of the electrons, the energy associated with their transitions, that's something we'll look at in chapter 7. And nuclear energy, yes, if you're a nuclear chemist or a nuclear physicist, that's important. Not as important to us, but if you're thinking about a particle, especially if it has more than one atom, we have lots of pieces of energy there to think about. If it's just a single atom, then you would have the translational, electronic and nuclear, because you wouldn't have any bonds that have rotation or vibrational. To find out the total energy, we would have to know, at a point in time, each contributing factor. We'd have to know the total translational energy, which is kinetic, the total rotational energy, also kinetic, the total vibrational energy, also kinetic, all the electronic energy and all the nuclear energy at that point in time. Hopefully it makes a little sense that it's not really possible to do that. We'll have a statement on another page in subsections of it, but to know all of them at once is virtually impossible. Okay? You could statistically figure out a probability it's about this, but you don't know for sure because in an instant, it's going to change. All right? And think that's one molecule. Imagine if you have a mole. All right? We already learned a little bit in the last chapter how it's average kinetic energy going on. And so therefore, if you hit more than one particle, they're not going to have the same kinetic energies as is. So it's impossible to know, meaning in this chapter we're going to be looking at changes in energy. How does it change? And that will tell us things. Does it go up? Does it go down? And things like that. Anybody else? Meaning we're going to move on to the next page and think about our translational energy more. Like I said, the first 3 sections and 6.5, we're thinking about that more than anything else. We kind of think about our energy simply, and not just in class, in chemistry in general. We know that energy, hopefully we know that energy is the capacity to do work. I like the second definition, the capacity to direct energy change resulting from a process or to move matter. We can write this as a simple equation. They have typed out for you energy equals heat plus work. We're going to look at work and look at heat and see how they're both translational energy, but how they're different. Any questions before we do that? Notice they're the arrows with particle on one end. We're having matter move. If it's work, we're moving all the matter in the same direction versus its heat. The mass, macroscopically, isn't moving, but the particles are moving. So they're moving in random directions. So as far as diagramming, that's up to you. You have access to the slides, that's fine. You could say slide 6 if you want to. But as far as C and D, you're asked to put it into words. So using the particle, what's another way to define work? Well, I wrote moving matter in the same direction. If I pick up my cup and I walk with it, I am doing work to move that matter in a single direction. Macroscopically, we see the mass move. As far as heat, using the particles, what's another way to define heat? Moving matter in random directions, meaning macroscopically, it doesn't move. But at the particle level, it is. The jittering and jiggling of particles. You want to think of it like that. In this class and the next class, we focus most of our time on heat, even when it comes to our chemical energy. Just so you know, work will come up a couple times, but we'll have to calculate with work. If you skim those sections, you would have seen that there was a little work in the book. Calculating work, we will not have to do that. And we'll remind you about that in a little while again. We good? Before we focus on our heat. So number 4, at the macroscopic level, heat is defined as the transfer of thermal energy between two bodies at their different temperatures. So I have a coffee cup. I've zoomed into the particle level a little bit, but why will your coffee or your hot tea get cold over time? Because the particles that are warmer have higher average kinetic energy, and the collisions with the barrier or the inside of the coffee cup is going to translate that energy or transfer it out of the coffee cup. So coffee particles have higher average kinetic energy, they collide with the container wall, and they transmit the energy to the surroundings. Does temperature equal thermal energy? Temperature is a measurement, right, using a thermometer. We put these 2 statements at the bottom of the page because some students had confusions. We found that out through our research. So no, temperature does not equal thermal energy. Also, does temperature equal heat? No. Heat equals thermal energy. Heat is the transfer of thermal energy. So heat and thermal energy you can associate with each other. Temperature is just a measurement. We use that measurement to tell what happened. The temperature went up, that means thermal energy transferred into what we're taking the temperature from. If the temperature goes down, that means the thermal energy transferred out of what we're taking the temperature of. We're now going to define some simple definitions. And again, I said we really do make these definitions as simple as possible. First off, we already have our energy is heat plus work. On the next page, we're thinking a little bit more about how this energy is being transferred, and then we can see we have a list of definitions. So I even went further into the particle level to kind of address number 5, although we kind of already talked about it, How is thermal energy actually transferred? Think in terms of the particle. It's transferred through collisions. We talked about the coffee pot particles colliding and transferring their energy. Well, if we have high temperature here, we have lower temperature here. Notice this peach particle at the bottom has a very long green arrow. We've already talked about how that can give us an idea as to how much energy or kinetic energy it contains. Notice when it hits the surface and bounces off, the arrow is shorter. That means it lost energy. Where did it go to? Well, the blue particle has a short arrow. When it collides with the surface and bounces off, it has a longer arrow. The energy was transferred from the hot side to the cool side through the collision of particles with the surface. Overall, we will have transferred in both directions, but because of the higher temperature side, we have a higher average kinetic energy and more collisions, there will simply be more transfers that way than that way, meaning net overall, we have heat going from hot to cold. I hope that makes sense. Things will just spontaneously warm up if they were cold. You have to have that heat coming from somewhere else. Now think about that somewhere else. We have this list of definitions. And I'm going to need my paper now. So I'll just give us a second. We can see that we have some definitions for systems, surroundings, and universe. And then we have specific definitions for the systems themselves. Before we actually look at the definitions specifically, again, make this as simple as we can. If we think of everything we know about contained in that circle, this would be our universe. Within it, there is something that we're very interested in. That would be our system. Everything else is the surroundings. They ask you to diagram an example of each of these if you want, and then I use the space, the cutout of the table, to think about all of them put together. So the system is a specific part of the universe that is of interest to us, to study, to understand. Let's say you're running a chemical reaction in lab. The reaction itself will be the system. Everything else, including the solvent in the beaker, the lab room, the chemistry building, UWM, the Earth, the galaxy, the universe, everything else is the surroundings. And the universe is just two of them put together. We'll do the system definitions, but if you look at the bottom page, it makes sense just to say this right now. What is another way to represent the system, the surroundings, and the universe using an equation? The universe equals the system plus the surroundings. You'll see SYS and SURR a lot, so I'd like to introduce those abbreviations right off the bat. You won't see universe as much. If we think of our systems, we can, of course, think of there's different types. I like this image, or you can just simply think of a drink container. That's why I like this image. Over there for you guys. An open system is a system that can exchange mass or energy, meaning the stopper on the bottle could pop off and the bottle could fall over. Or I could accidentally hit my metal straws. They don't bend, the bendy straws, and also the whole thing falls over, and I can lose my water. My water can also get warm over time. So we're having an exchange of both mass and energy. If we make sure that we have our bottle closed really well, or right when you buy it before you broke that seal, that's like a closed system. You're assuming nothing is going to leak out of or leak into your bottle. However, the cold soda you buy at the grocery store or the gas station could still get warm. Isolated systems are like ideal gases. They're theoretical, but we learned that we can treat gases in real life as ideal if we don't have a lot of them in our box and they're at a sufficiently high temperature. Well, we can assume we have an isolated system lots of times. Isolated systems, nothing is entering or leaving, no mass or energy. It's like that absolutely perfect insulated coffee cup or an insulated travel mug that will keep your coffee or your tea hot for years. It doesn't exist. But we will actually use isolated systems lots of times to make the math easier.
about the system and the surroundings, the system can, of course, either gain thermal energy or lose thermal energy, right? It could be if it's either open or closed. If it's gaining thermal energy, where is it coming from? What's that here? The surroundings. It seems like a simple question, but to understand if your temperature of what you're measuring increases, that heat had to come from somewhere. The only place it could have come from is the surroundings. We keep it nice and simple because it is simple. If you don't overcomplicate in your brains, it makes sense. We are going to look at some slides now that have a bunch of stuff on them, so I'm going to, remember which button to push? We'll come back to the paper in just a second. We're going to define terms for if the heat is going into or out of our system. So in number 9 and 10 is what we're talking about. If you didn't turn the page, number 8 is the question I just asked, but I didn't reference turning the page because I want you to think about it. So in number 9, we have the definition endothermic. System gains heat, or there's a transfer of thermal energy from the surroundings to the system. Meaning if you're measuring the temperature of your system, the temperature's going to go up because heat entered our system. Heat, therefore, would be a positive value. WRT means with respect to. It's a very common abbreviation, it's not just me. So WRT with respect to the system, heat is positive. If we're gaining heat in the system, that means the surroundings is losing it. So therefore, with respect to the surroundings, heat would be negative. We're going to push a button, lots of things are going to come up, we'll talk through it. So if our heat is positive and Q is our variable for heat, that would be greater than 0. Because it's going up, which means our final temperature would be greater than our initial temperature. They have the TF, the TI type for you. So the inequality would be the alligator eating the final temperature. Therefore, our change in temperature would be greater than 0 because it's warming up. Whenever we do a change in a variable like this, we always see the final minus the initial. So it wouldn't make sense to say the change is going down if it warmed up. I do have 2 examples for you, a physical and a chemical. The chemical is first. If we want to decompose mercury 2 oxide to its elements, we have to add energy in the form of heat. If we want to melt an ice cube, we need to put it in an environment that's warmer, and therefore heat will go into the ice cube. You put an ice cube in your hand gets cold. Why? Because the heat in your hand went into the ice cube. As far as diagram, your middle box, this is what they're referring to. Again, don't overcomplicate it. If your system is that box we had drawn before, although I think I drew a rectangle, but a box of some sort. If it's endothermic, heat is going into your box. The surroundings are outside your box. Sometimes we do have to complicate things a little bit though. What's over here is called an energy diagram. You're going to be seeing a lot of them in your future. They don't go away, as I keep telling my Chem 104 students. Every chapter they show up. Energy is the y-axis, reaction progress is the x, meaning reactants are over here, products are over there. If we're putting energy into the system, and this is an endothermic process or reaction, the energy content of the products is going to be greater than the reactants. So products have a higher energy versus the reactants is lower because we had to put energy or heat into that system. Please note there's always an energy barrier between reactants and products. As you'll learn next semester, there's a lot that goes on in between looking at reactants and going to products. Breaking bonds, making bonds, reorganizing atoms, and all that kind of stuff takes energy. So we'll always have a hill between our reactants and our products. A nice way to remember endo is the beginning of the word, enter. If you enter the lecture hall, think of the heat is entering the system. Are there any questions about the slide or the little table? If heat is leaving the system, like the opposite of everything is going to go on. We call that exothermic. A lot of students actually are easier to remember this one, and I purposely made the word red because you always see red exit signs. You're leaving the lecture hall, heat's leaving the system. System loses heat. There's a transfer of thermal energy from the system to the surroundings. Therefore, with respect to the system, our heat is negative. When you think in math, you're subtracting some energy content from the system because it's going to be cooling off. Our final temperature is going to be less than our initial, which means you're going to have a drop in temperature, therefore the change is negative or less than 0. And again, Q is our heat. I forgot to say that. I said it's negative, but I forgot to reference the Q less than 0 popping up there. As far as my examples, again, a physical and a chemical, I've included the chemicals first. If we want to make water from its elements, we actually have to remove energy, meaning energy comes out. Hydrogen and oxygen explode, and you get water. That energy can be used for many things, such as powering fuel cells. As far as our physical change, if we want to condense water vapor to liquid water, we need it to cool off, which is why we want a sufficiently high temperature for our ideal gases. If they're too cool, they start to condense. Energy is leaving the system as they condense, because they have to cool off for that process to occur. Hopefully what I call the box diagram, the simple one, makes sense. The arrow is leaving the system. Therefore, the heat is going to the surroundings. And I know energy diagrams are newer, but hopefully it makes sense. Your products have less energy content than the reactants. Where did it go? It left the system and it went to the surroundings. Questions? Purposely, I'm trying to rush this because I'm assuming it's new. By the way, that was section 6.1 and 6.2. We're moving into 6.3. We are going to do some theoretical work. Sorry, we have to do some. The practical applications come for the rest of the chapter. So if you turn the page, we have definition, not on the screen, but on our page for thermodynamics in number 11. This scientific study of the interconversion of heat and other types of energy. In order to study these changes, we study the state of the system or the properties of the system. Those are called state functions if they behave in a certain way, and they're called non-state functions if they behave in a different way. In order for something to be a state function, you could also call it a state property if you don't like the word function. I know it reminds you of scary math. A state property are properties that are determined by the state of the system, regardless of how that condition was achieved. And I like to tell a story that relates to things you've been doing lately. Let's say you were in lab, and you're doing your titration experiment, and you had gone to the main hood, and you got your, I think it was 50 milliliters, if I'm wrong, sorry, of acid, and you put it, you had it in graduate cylinders, you had measured out dyes, and you sat down, and you went to go get the base to fill up your burette. And all of a sudden you come back, and your graduate cylinder is halfway empty. If it was 50 milliliters to start off with, and it's halfway empty, what was the change in volume? 25, right? Did you need, yes?
Is the U?
Well, let's get to the U. So the change in the volume was 25 milliliters, because I said it was half empty. Did you need to know how it changed? You'd like to know who messed with my acid, right? Who took some of my acid, but you don't need to know. You just need to take the big amount and subtract about half, and you got to 25. And you knew it went down, so the change in volume would be negative. That's how all state functions work, meaning they are, it's determined by the state of the system regardless of how that condition was achieved. I say it's independent of path. Now, there are several state functions up on the screen. We have energy, pressure, volume, and temperature typed up for us. We also have it in variable form. In our textbook, our author uses U for internal energy. So the change in internal energy is simply equal to the internal energy at the end minus the internal energy at the beginning. Does that answer your question? I didn't want to confuse others by stopping my story halfway. I knew I was going to say it in just a second.
I don't know, I didn't understand it. U actually controls that.
Other books use E. I don't know why he uses U. Don't know. U is a common variable for internal energy, meaning not all the energy internal to the particle, but E would make more sense, I know. Change in pressure, final minus initial. Change in volume, final minus initial, change in temperature, we already talked about, we always take the final minus initial. In order to understand this path idea, the two hikers at the top of the mountain, okay, they're at the same altitude, independent of the path they took. We could determine the change in altitude between where they are now, let's say base camp, through simple subtraction. We don't need to know which path which hiker took. However, if we want to know the amount of work they put into climbing the mountain, then we would have to know which path. Work would be a non-state function, meaning it would be dependent on the path taken. I'm going to have to go back to the doc camera for a second. So if you're thinking about that red path, you might think it's easier because it doesn't seem as steep, but it's longer. The blue path seems a lot shorter, but it looks a lot steeper. Meaning, if you could argue about which path used less work, that means it's not dependent on the state of the system alone. I'm going to write out quick definitions for state function versus state non-function, or non-state function. So again, just so we have it, instead of just talking, we have it written down. A state function. And my quick and easy definition, yes, there are longer ones, are independent of path. You could calculate the change in volume of a graduated cylinder through simple subtraction. It didn't matter how it changed, no matter what path was taken to change the volume. Whereas a non-state function, you could use the word property also if you want, is dependent on path. Do you think the time it takes for you to get to campus every day would be a state function or a non-state function?
Non-state.
Not, because it was dependent on what path you took. If you lived nearby, you took bus versus walked versus had somebody pick you up and drove you here, and the bus broke down. If it's snowing and walking just took forever, it would depend on the path taken. So just give you an idea of a real life non-state function versus the real life in the lab change in volume or a state function. We good? We're going to be thinking about the first law of thermodynamics now. This is the theoretical part. Don't worry, there's not a lot of it. So we're going to think about this in terms of the energy of the universe. So U sub, sorry, it's on your sheet. That was typed up there. U sub U and IV. We're going to think about the first law of thermodynamics in terms of heat and work. And then we're going to think about the first law of thermodynamics in terms of the energy internal to the system versus the surroundings. Anybody know the first law of thermodynamics in words?
Is it that energy can't be created or destroyed?
Yeah. The law of conservation of energy. We just like to make it sound like it's harder by saying the first law of thermodynamics. So energy cannot be created or destroyed, which is why we already get the idea that if our system got warmer, the heat had to come from the surroundings. It couldn't just magically appear. Or if it cooled off, the heat had gone somewhere to the surroundings. It can't just magically disappear. So we're going to do this in terms of a very simple system. We just have two particles. And this is the same system. It's before and after. So the 1 is before, the 2 is after. We can see at the beginning, our first snapshot of this system, we have a fast-moving particle traveling, what seems to be, towards a slower-moving particle, and we have possible trajectories, although there's other ways it could go, those dashed arrows. Our second snapshot is obviously after the collision, and we can see how our labels have changed. The open circle, which was initially fast-moving, is now slow-moving. And our filled-in circle, which was originally slow-moving, is now fast-moving. So there's been a collision and a transfer of energy. Can we measure the internal energy for just one particle? That's an S. Can we measure U sub 1, or we'll say, or U sub 2? And it does give you a reference to think about number 2A, which was that red equation on the bottom of the slide, and we talked about that we could possibly get little bits, but to know it all at once is impossible. So no, we cannot know the energy internal to the system, let alone a particle. So this is no at the bottom of your page. This course continues. possible, underlined, to measure all these contributions accurately. So we cannot determine the total energy internal to a system with any certainty. Changes in energy, therefore, as we've already said, but just in case we haven't got it yet, can be determined experimentally by simply looking at the thermometer most of the time. We're going to go on and think about our first law of thermodynamics in those three different ways now. So number 15, if this is an isolated system, does use of one equal use of two? Isolated energy cannot enter or leave. And obviously we've kept the same amount of matter, two particles. So number 15, use of one does equal use of two if isolated. That is true. We're not losing any energy, we're just transferring between the particles. What is the change in internal energy to this system equal to? First in a generic sense, and then I'm going to do it in terms of a reaction, and then we're going to do it in terms of this system. So in a generic sense, the change in internal energy, move up a little bit, for a system is equal to the final minus the initial, meaning for this particular one, that would be 2 minus 1. If this was a reaction, the change in internal energy for, you want to do that, for the reaction would be equal to, what do you think the final state would be for a reaction? Products. And the initial state would be the reactants. In terms of our specific system, if our use of one equals use of two, if we subtract the two numbers, whatever they are, what will be the answer? 0, right? 10 minus 10 is 0. 100 minus 100 is 0. Doesn't matter. Again, if isolated. We were asked for the generic one, we were asked for reactions, but I also wanted to think specifically about this one. What is the first law? What if the system was equal to our universe? Meaning, what if that was our universe? The change in internal energy for our universe is equal to 0 if it's isolated. So, for number 18, I know I didn't reference each one because some will blend together. If the change in internal energy for the system we've been talking about equals our universe, that means the change in internal energy for our universe equals 0 if isolated. This is the first law of thermodynamics in terms of the energy of the universe. We are under the assumption that our universe is isolated. If there are multiverses, I'm not saying they're not, but we're saying there's no transfer of energy into or out of our universe. Meaning the amount of energy we have now is the same amount of energy we had whenever it began, however you think that happened. So this is both 18 and 18A. Any questions with that one before we move on to the next one? I also have to change a piece of paper, so I'm just waiting a second. We're going to move on to 19, which is now we're going to think about the heat and work definition. So, because the system is isolated for number 19, what is change in use system also equal to? Well, we have already written that, or we saw that energy, wow, got my G, there we go, equals heat plus work. Well, if it's isolated and we're just thinking about the energy within that system, the change in internal energy for the system would also be equal to Q, the heat, plus W, the work. That is the first law of thermodynamics in terms of heat and work. And we can define energy in different ways. We can think about the change in the energy for the universe. We can think about what the energy of our system is comprised of. But if Q goes down, that means W has to go up, because we have an isolated system. The change has to stay the same. Meaning, I'll add that to the end, equals 0 if isolated. If it's an isolated system and you know the Q, you also know the W. you why we like isolated systems. Makes everything very easy. Now we're going to think about the first law of thermodynamics in terms of the energy of the system, relating that to the energy of the surroundings. So, given delta U of universe, before I just said universe equals system plus surroundings, equals delta U of system plus delta U of surroundings. And we know that this equals 0 from our other definition of the first law of thermodynamics. Now put that reference there. Delta U of universe equals 0. Now we can think of within our isolated system, we can have another system. Meaning the particles' interaction compared to the empty space around them. We will have to think about this when we think about calorimetry. You're going to have an isolated system, but inside you're going to have a reaction, let's say it's in water. The reaction would be the system inside the system, and the water would be the surroundings. I know before we defined these two as the same. Now we're thinking about a small system within our isolated system, which we call the universe. What is the first law of thermodynamics in terms of energy of the system versus energy of the surroundings? Well, if this equals 0, I can solve, let's say, for delta U of system. Subtract that from both sides, has to equal negative delta U of surroundings. If I wanted to solve instead for delta U of surroundings, that would equal negative delta U of system. That is the first law of thermodynamics in terms of the system and the surroundings. Again, it depends on what we're thinking about as to which ideas we would use. All of them are conserving our energy though. We have one last little thing to do today. Any questions? You gotta give them a little more on the questions. This is table 6.1 from our textbook. And don't ask me why the author in number 21 on page 192 decided to flip things around and do. I think they wanted to have the more familiar terms at the top of their table, but for that table, the key part, the more familiar terms, are at the bottom of the table. Sorry about that. So I'm going to follow the order for the table on your sheet. We'll reference the one from our textbook. So, the first row in number 21, we're thinking about if things are positive or negative here, and then about box diagrams. Heat absorbed by the system, which is an endothermic process. Heat is going into our system, so we would have a positive Q. Variable Q would increase if you add something to the heat that's already in that system. Which means when we have our system surroundings box, the arrow going in is the heat. And that's referring to the third row on that table. If we have an exothermic system, heat absorbed by the surroundings. That's a weird definition for me because I like to think about the system. So if you prefer to think about heat being lost by the system, that's also exothermic, and that was our definition from before. Which means the heat content within the system would go down, minus Q. And I kind of made that a little too high. So I move my box down a little bit. System, surroundings, my arrow, my heat is leaving. I'll have to make sure to get the next two straight. The unfamiliar ones, the ones at the top, sorry, that was referring to the fourth one in the table from the book. The unfamiliar ones work. They're at the top of the table from our book, the bottom two on the table in our sheet are referring to the work. So look at the bolded word for the third one. Work done by the system on the surroundings. If the system is doing work, and work is part of energy, it's going to use up some energy, right? Meaning the energy component that is work is going to go down. So it's a subtraction term. The system is losing some energy due to doing this work. It's kind of hard to think about that for some people. If our system is going to be gaining energy in the form of work, that means the work is being done onto the system. If your system is a gas sample in your gas laws lab and you're pushing the piston and compressing that gas, you're making a smaller volume, there's going to be more pressure, you're giving energy to that gas sample. You're adding energy in the form of work. Meaning for our box diagram, my arrow is going in for the work. And we already talked about the first law of thermodynamics being the law of conservation of energy, in case it's typed up there as well. But right underneath the table, aside from the sign convention for work, we will not do work, meaning information on page 184 to 186 of your textbook are things you don't have to worry about. Those are what I mentioned earlier, some calculations and stuff like that. You will not have to do that. You can see the rest of page 92 are some of those problems that I had already put on the lecture activity page. By the way, the Moodle problems are a lot of things about heat and work. So this table will be very helpful to do those Moodle problems as well. Sign conventions and thinking about which way the energy is moving. Next time, we are going to be getting into 6.5, which is calorimetry. And it's calculation based, it's the practical